Lecture 4, Processes. Early computers, as well as a number of modern embedded systems, did exactly one thing, or at the very least, exactly one thing at a time. And at that time, the program that was running had access to all the resources available in the system, so managing resources wasn't such a big problem. Now, of course, your modern operating system supports many different programs running concurrently. You would not accept it as okay, for example, if you had to close an application before you were allowed to open another in your operating system, even on your phone. Like, that wouldn't work. You want to be able to have multiple things open at the same time, even if you might only be paying attention to one at this very moment. Certain things do need to be able to continue in the background. So, to manage this complexity, the operating system uses the concept of a process, and we have, of course, already worked with them, but we may not simply have known that at the time. The formal definition of a process is it is a program in execution, and it is composed of three things. Number one, the instructions and the data. Notably, the compiled executable is the program, and that is only one part of the process. The current state, that is where we are in execution of this process, and any resources that are needed to execute. And that's files, that's memory, that's anything that counts as a resource that is open or in use during execution. And if we have two instances of the same program running, those are two distinct processes. So you can have two windows open for Microsoft Word. Even though they're the same program, it's the same executable file, word.exe or equivalent, they are considered different processes because they are at different points in their execution. They are managed separately by the operating system. They share the executable program, but that's only one part of the process. Similarly, two users who both use Firefox, the browser, at the same time on a terminal server, they also have two different processes. Again, same program, but different processes. So here we have two documents here that are open. On the left side is some text, document 1. On the right side is some text, document 2. And they are, of course, distinct because they are completely different in their state. You can be editing in one of them on the right side, and it doesn't affect what's going on the left because they are different processes. We're going to take a slight detour to the behind-the-scenes view of how the operating system manages a process, just so we can have a little bit of a mental model of what's happening when a program is executing. The operating system's data structure for this is the process control block, and it is a data structure containing what the operating system needs to know about that program in order for it to run. It will be created and updated by the operating system for every running process, and it can also be thrown away when that process is no longer running, when it's finished executing and everything has been cleaned up. And these blocks of the process control blocks, that is, are held in memory and maintained in some container, a list, or some such by the operating system kernel. The process control block is how the operating system is going to think about it in terms of scheduling. It's also how it makes sure that if you forget to deallocate memory, that memory gets cleaned up when when the process is no longer running. Same thing, files are automatically closed. It's all managed through the process control block. And a process control block will usually contain the following fields. So it has an identifier. This is a unique ID associated with the process, and that's usually a simple integer, and it will be incremented when a new process is created, reset when the system is rebooted. We will see later in Unix that identifier is just a simple integer. They can eventually get reused, but they are at least relatively unique. That is, two processes can't have the same identifier at the same time. State. The current state of the process. We're going to spend some more time later talking about state specifically, but you can think of it for now as to, is it running? Is it waiting for something? The state is probably the most important thing that we want to take away from this discussion. Priority, how important this process is, and that's relative to others. Program counter and register data show up on here with little asterisks. That's because they are not kept up to date constantly. They're updated only when needed. So the process control block is a place where the current program counter, that is where we are, what is our current instruction, what is our next instruction, and the register data, the values that go in the registers, can be stored when switching between processes. And memory pointers, this allows the operating system to keep track of what memory has been allocated to this process or by this process. I/O status information, are we waiting for anything? Do we have a file open? Are we waiting for an I/O operation? Is a device assigned to this? And then there is accounting information, so this is data about the process's use of resources. In a technical sense, it's optional, but basically every operating system will have it. The idea being that we have to keep track of how much CPU time it has used and what resources it's consuming, because those sorts of things are helpful and may be used in scheduling policy as well as in just making sure the system is working for multiple users. On an ECE run server, we could have hundreds and hundreds of users, and accounting information is used to make sure that no one user is monopolizing the time of the system. If you wanted a simplified visual representation of that, the process control block, it's just a sequence of fields, and it can be as many fields as are needed. And as I said, everything is kept up to date with the exception of program counter and register data. They have little asterisks next to them. And when the program is running, you don't update those values every time. However, it will be used when a system call or process switch occurs. And this is how we effectively store and restore the state of the program as the operating system. So save the state of the process into the process control block, so the program counter variable and the register variables, and we'll end up with some workflow that looks a little bit like this. So here is a sequence showing that process P0 is executing here at the beginning of time, and there will be an interrupt or system call of some sort. Save the state for this process into its process control block, and in the three dots here, the operating system is doing whatever it needs to do. That may be carrying out a system call. It might be the scheduler is running. The scheduler in this case will decide that process control block 1 is going to execute, and so it will reload the state from process control block 1 and restart process P1. P1 will then continue and execute for some period until it gets to an interrupt. Say it's a system call, or maybe it is a timer interrupt, that its slice of time in which it gets to execute has expired, and we will save the state. Again, operating system will take some actions, decide which process should run next, reload the state from process control block 0, and then execution resumes here on process P0. As you can see, there is a large amount of time when neither process P0 nor P1 is executing. This is generally undesirable, and the goal of the operating system, as we discussed, is to let your programs run. It's not supposed to focus its time on running itself. It's supposed to help other programs to execute, and so it's important in operating system design to try to minimize the amount of time that it takes to do things like decide which process is going to be next to run, because ultimately the useful work that's being done is quite limited in this diagram. If you add up the blue arrows for P0 and P1 and you compare it to the total fraction of time that's represented, it's not great. So we would prefer, all things being equal, to have fewer interrupts and to have the operating system do less, but obviously we know some things cannot be avoided. So you may be wondering how to decide which process gets selected next. That's a complicated question. As I've mentioned previously, there is a whole course topic coming up towards the end of the course around scheduling. And a lot of scheduling is really based around this idea of how do we choose which process runs next. There's going to be many different options that we consider. For now, and maybe just for a lab, let's imagine a simple scenario where process control blocks are kept in a data structure, and the operating system can iterate over those process control blocks to figure out which one is next. In a really, really simple approach, the PCBs are in an array or a linked list, and we just iterate over this collection, and we remember which of the process control blocks we've seen has the highest priority and isn't currently blocked. that may work. If you want something a little fancier, a little more complex, takes a little more space, then we could have a priority queue system with different queues per priority. The advantage of that is it does make it meaningfully faster to dequeue the next ready PCB rather than the linear behavior we would see in the super simple approach. But is the super simple approach totally insane? I mean, we're just always taking the highest priority task that's ready, right? We're not necessarily giving consideration to any other task. We're just saying, okay, whichever one is the highest priority, that's what we're going to do. Is that insane? I'm going to say no. This is one of the algorithms we will discuss later in scheduling, so it's not totally ridiculous, right? Whether it's optimal or not is a different discussion. It's probably not. But optimality is difficult to define in something like scheduling because that's a question of how well does it achieve the objectives of the scheduling system. But we're getting ahead of ourselves, so let's come back to that later. For now, for something like a lab where you just need one simple strategy, this is one that you could use. Okay. And processes have a circle of life. Unlike energy, processes may be both created and destroyed. Upon creation, the operating system creates a new process control block for that process and will initialize its data. This means set the variables to their initial values, what is the initial program state, and the instruction pointer is moved to the first instruction in main, and then the process control block is added to the set. After the program is terminated, we can collect some data, a summary of the accounting information if needed, and we can remove the process control block from the list of active processes and then carry on. There are, generally speaking, 3 events that lead to the creation of a process. Number 1 is system boot up, so some things are started kind of automatically when you start the computer or when you log in. Some are by user request, so you as a user say, I want you to open the text editor, or you ask it to start the compiler. That's creation of a process by user request. And then there is one process spawns another without direct user intervention. So at boot up, when the computer starts, the operating system begins running and it creates some processes. If it is an embedded system, it is the anti-lock brakes controller in a car, then whatever processes, if there are any other than the main one, it has all the processes it will ever need. NASA Mars lander might have the same thing. It has 5 processes that it's going to run, and they're all started at the beginning of the operating system boot up, and there are no more, and there's no other way to start them because they should always be running. A general purpose operating system, your typical desktop or laptop or phone operating system, allows at least one, but almost certainly both of the other ways. First is users, and second is processes spawning another. But some processes, regardless really of how they're started, will be in the foreground and some in the background. And the difference between this is basically, can you as a user interact with it directly? So a login process, the login screen where it presents, please enter your username and password, that's user visible, and we would say it is foreground. If you open a PDF viewer, that is a foreground process because you can see there is a window on your desktop in which the PDF is being shown. That's a foreground user interactive process. There are also background processes which you don't interact with directly, but you can interact with using some client. So if you have a server that shares media on the local network, that's a background process. The Unix term for this background process is daemon or daemon. As far as I can tell, both pronunciations are considered acceptable. And a good example that you should at least have tried out if you did the GitLab setup stuff by now is the secure shell daemon. So if you want to log into a system, say EC Ubuntu, you use your client, the SSH client, the command for which is SSH, your username at this URL or this address. And on the receiving side, there is a background process, the secure shell daemon, and it is awaiting incoming connections. When you attempt to connect, your SSH client connects to the remote SSH daemon, and it responds to your connection attempt by saying, please provide your username and password, and verifies those, and if they are valid, then it connects you to a session. Okay, users are well known for doing whatever they want without necessarily consulting with you or without the approval of operating system designers. So every time you double click an icon, enter a command on the command line, like SSH, it results in the creation of a process. This image really makes me sad because how could you ever find anything in this horribly disorganized mess? But users can do that even if it's not what the designers of the operating system intended. Okay, I can't look at this anymore. We have to go on. The last thing, and this is what we're going to really spend our time on in this course, is the idea of processes creating another. So an already executing process can create one. If you get an email and the email contains a link, first of all, you should never click it. It is dangerous and unsafe to click links in your email, and you shouldn't do that. And so my security advice is don't. But if someone did, not you wouldn't make this mistake, but if someone clicked a link in the email, then the email program isn't a web browser, and it wouldn't try to render the web page the way a web browser does, because it doesn't really make sense for it to do a thing that's not its job. So what it will actually do is start the web browser. It will say, hey, this isn't my area, I would like a different program to handle this, and that would actually work. Now, a program can break its work up into different logical parts without necessarily being, we need to invoke a different program altogether. We can say, well, we're going to split our one single program into, say, a client and a server part. And this could be used to either promote parallelism, the idea of getting more work done at the same time, or fault tolerance. So if the client crashes, we can restart the client, and that's fine. The server remains up. When that happens, we are thinking about creating a new process programmatically, so from within an already executing process, and that's sometimes referred to as spawning. The process that creates the child is the parent, and the newly created one is the child. We'll return specifically to the subject of relations between processes in Unix a little bit later on. But just keep in mind that there is a parent and child relationship between processes when spawning occurs. Eventually, most processes do die. I mean, some of them continue on for basically ever, but or until system shutdown, but they can die. This can happen in one of four ways, and some of them are good and some of them are bad. There's normal exit, which is voluntary, error exit, which is voluntary, a fatal error, which is involuntary, and a process can also be killed by another process, which we would also consider to be involuntary. So most of the time, the process finishes because it's actually done, right? Or the user asks them to. If I was editing a document in Notepad and I said save and exit, when I clicked on exit, that's a voluntary normal exit. This is a normal voluntary termination. Why is it voluntary? Because I chose it. The program didn't encounter an error. It's not unexpected. And it's a normal exit because it's not an error. I just said, I'm done now. I've finished editing this document. I'm going to exit. Sometimes you don't, as a user, have to make that specific choice. When the compiler finishes compilation, it terminates normally. It got to the end of doing all the stuff for compilation, and it says, yes, I'm done now, and I'm going to exit. That's great. And we should expect that most of the time that is what happens. Now, sometimes there is a voluntary exit, but with an error. And we already saw a code example of this where if you attempt to run the read file program, but you specify an invalid file, it will exit with return -1. That's an error exit, but it's voluntary. The program has said, well, I don't want to go on under these circumstances, so I'm going to choose to exit. And that can happen for lots of reasons. If the user tries to run a program and it requires write access to a temporary directory and you don't have permissions, it may exit voluntarily with an error code. And in whatever scenario we are imagining, it's a voluntary error exit if the program chooses itself to terminate, that is, not continue, because of an error, and that's voluntary because the program has made this decision. Then there is the involuntary error exit. And that is a fatal error has occurred in the program. So if you have a stack overflow error, a division by zero, segmentation fault, anything like that, something has gone wrong in the program. The operating system has detected the error, segmentation fault being we've tried to read memory that doesn't belong to us, or division by zero being an arithmetic problem. And this often results in involuntary termination of the offending program. It's not that we chose to exit, it's just we have stumbled across this error and we don't know how to handle it, so the program is terminated. A process can, of course, tell the operating system that it wants to handle some kinds of errors with, try-catch kind of behavior, in which case the operating system still delivers the error to the program, which will hopefully be able to deal with it. If not, then the unhandled exception or error does still result in the involuntary termination. You can catch these kinds of errors and then just proceed to a voluntary termination if you want. It gives you an opportunity to clean up a bit or print some helpful error messages before you exit, but that would change the type from involuntary, where it just dies due to this invalid request, to a voluntary exit, where you said, well, I observed an invalid request, but I'm now going to choose to tell you about it before voluntarily quitting. And the final reason for termination is that processes may kill one another. So murder is a thing in the process world. Is no one safe? Typically, this is actually a user request. A program is stuck or consuming too much CPU. The user opens Task Manager or looks in Unix with the PS command to get a list of processes, and then you choose to kill it because you think it's stuck, you think it's taking too long. Now, that's not the only way to do it. Programs can, without user intervention, kill other processes. If a parent process decides it no longer needs the result from a child process, or it thinks a child process is taking too long and it's stuck, it can use the kill command to actually terminate that other process. That's kind of grim. Sorry. There are obviously restrictions on killing processes, and that is a user or process has to have the rights to execute the victim. Typically, as a user, you may only kill a process that belongs to you, one that you have created, with the obvious exception of a system administrator. Killing processes might be fun, but it's something that should be reserved only for when it is actually needed. In some operating systems, when you kill a process, it also kills all the child processes. That's really cruel. Neither Unix nor Windows works that way. In Unix, a parent can outlive the death of its child, and vice versa. Now, in Unix, but not in Windows, the relationship between the parent process and the child process, or processes plural, is maintained, forming a tree-based hierarchy. And a process, unlike most plants and animals, reproduces asexually. You could think of it as being kind of more like an amoeba in that it divides in two identical pieces, as opposed to anything more resembling like parent and child. It's more like it just divides itself like an amoeba or bacteria or something like that. A process has exactly one parent, and it can have 0 or more children, and a process and all of its descendants form a process group, and certain operations like sending signals are a topic we will come back to when we talk about inter-process communication, can be sent to a group as opposed to just an individual process. Now, in Unix, the first process is usually called init, although in some systems init has been replaced with systemd. Same purpose, it's just a question of which implementation you have. And this is eventually, in the hierarchy, the parent of all processes, in the same way that the object class in Java is the superclass of all classes. If you send up the class hierarchy far enough, everything is a subclass of object, and in that same way, if you go to the parent process of your current process repeatedly, you will eventually reach init or systemd. And that means in Unix, you may represent all processes using a tree structure. That's not the case in Windows. In Windows, a process that spawns another gets a reference to the child, which allows it to exercise a little bit of control over the child, but this reference can be given to another process, meaning that the concept of adoption exists in Windows, but not in Unix, and there isn't really a strong hierarchy, whereas in Unix, a process cannot disinherit a child. It can't say, pretend I don't exist anymore. Now, when a process terminates, it does so with a return code, and we saw that previously in some code examples where we return 0 at the end of main, or we return -1 if something goes wrong. If you just run it on the command line, /a_out, it is ignored. The return value is there, but it's not used for anything. Same thing if you double-click on an icon in your operating system's graphical user interface. It starts the process, but you don't see the return code. However, in Unix, programmatically, the parent process can get the code that the child process returns if you want. It is, as the case with a lot of system calls, usually convention that return value of 0 indicates success, and other values will indicate an error of some sort. Normally, there is some sort of understanding between the parent and the child process about what a particular code means. There's no strong definitions about, well, does 5 mean this, or does 10 mean that? Those kinds of things are not necessarily determined anywhere except as agreement between the parent process and the child process, most of which you probably wrote yourself or in your team anyway. Fear the Walking Dead. Okay. When a child process finishes, until the parent collects the return value, the child process continues in a state of undeath that's referred to as a zombie process. Now, this doesn't mean that the process shuffles around the system attempting to eat the brains of other processes, entertaining as that might be. It just means the process is dead but not gone. There's still an entry in the PCB list, and the process holds on to its allocated resources, and it's really only after the return value has been collected by a parent then that PCB and all of its associated stuff can be collected. Usually a child's process's result is eagerly awaited by its parent, and there is a system call which we will examine soon, the wait system call, which collects the value right away. This allows for the child to be cleaned up, or if you want like extra grim terminology for it, reaped. There is the possibility of some delay for some reason. If that's the case, the process is a zombie for some amount of time until that value is collected. So seeing a zombie process in the list isn't necessarily bad. It just means that this has finished and it hasn't yet been collected, and that should happen sooner or later. If it doesn't happen for a long time, that's concerning. It means somewhere a parent process has failed to collect a result from a child, but that is usually fixable. Now, if a parent process dies before the child does, then the child process is called an orphan. And in Unix, any orphan process is automatically adopted by init or systemd, which makes sure eventually that all processes have a good home. The default behavior of init in this scenario is to just collect the return values from child processes and do nothing with them, thus allowing them to be cleaned up. And you can, of course, choose if you wish to intentionally orphan a program. It allows it to run in the background. That might be cruel, except, of course, processes, as far as anyone knows, do not have feelings. Now, as you might imagine, at any given time, a process has a certain state, and in the simplest possible view, we would say that the process is either running or not running. So if we were to develop a model of what does the process state look like, the first two states of the model are probably running and ready. That doesn't account for everything that we already know about. For example, a program that requests a resource might not get it right away, and that gives us the blocked state. So based on what we know about processes already, it could be running, it could be ready to run, but not actually running right now, so it's waiting its turn. Or it could be blocked. It can't run right now because it is missing some resource or something that it needs. We did not, however, cover in this three-state model the concept of zombies, and just as a life pro tip, if you've watched enough zombie movies, you will know that the character who doubts that zombies are real is the one who dies first, and therefore it is in your self-interest to always believe in zombies. So we need a state to represent that as well, otherwise our model doesn't match what we already know. And we can't use blocked for this because the process is finished, but its value is not yet collected, but it's also not ready to run, and it's not waiting for a resource either, so it wouldn't really make sense to call it blocked. So we need a new state for that, and that would be terminated. Okay. You might have noticed, if you were paying attention to the titles of the slides, that it says 5-state model, and we have thus far only covered 4. So spoiler alert, there is in fact a 5th state. And the 5th state is new, that is, just created. If the user creates a process, the operating system does have some work to do, like define an identifier, instantiate the process control block, put it into the new state, all that sort of stuff. The operating system has created it, but it hasn't really started it yet, and it hasn't committed itself to the actual execution of this process. This could be because the operating system limits the number of concurrent processes for performance reasons, and you can't start 10,000 things because it would slow down the system too much. So a process that's in the new state is kind of waiting its turn, waiting for there to be available time in which to run it. So the other thing is new processes are typically on disk and not loaded into memory. So if the process is, we've acknowledged the request, but nothing has happened with it yet, we haven't actually loaded the program into memory or anything, then the new state is appropriate for that. So with our states, as we've discussed them so far, we have running, ready, blocked, new, and terminated. And if we look at the transitions between them, when we create a new process, it goes to new. When it's going to be prepared to be started, we can put it in the ready state. When the scheduler chooses to run it, its dispatch transition puts it in running. It could get blocked, or it could be suspended, and it could be finished, so it goes to exit. Now, this diagram is missing a couple of additional exit transitions. A process that's in the ready or blocked state could transition directly to the terminated state. If a process is killed for some reason, even if it was blocked, that moves it straight to terminated, and it just prevents cluttering up this diagram too much. And there are 8 transitions in the diagram: create, admit, dispatch, suspend, exit, block, unblock, and reap. And I mentioned the 2 additional exit transitions. We can also expand on the 5-state model by considering the idea of disk, because a process might not be entirely in memory, specifically because users might request more things be running than actually fit in available memory. The limiting factor is not the process control blocks. They're not that big. It's the stack and the heap space of the programs. With no other place to put them, the operating system will put parts of processes on disk, and that's what's known as swapping. When demands for memory exceed the available memory, parts of processes will be moved to disk storage to make room, and that is a notably expensive operation. Disk is slow compared to memory. Swapping is, how slow is it? Well, you might recall I mentioned earlier the idea that if we have to get a page from disk, it's the equivalent of having somebody walk it from the Library and Archives Canada all the way to Waterloo. Takes quite a while. So from the perspective of the CPU, it takes like 7 eternities to actually write things to disk, and then if we're going to have to read that in again, it takes again as much time to read as it took to write. So swapping is undesirable, but it will happen when it is only necessary. And the idea of that 6th state for something being swapped is to make sure that the operating system knows which processes are currently in memory and ready to run and which ones are not. Ideally, a process will only be swapped to disk if it's blocked, and it remains blocked and not in main memory. But of course, when it's on disk, it could be ready as a result of something that happened. It was waiting for an I/O operation to finish, or was waiting for the user to press OK. Or what if all processes are ready, but there's just a shortage of memory space altogether? So the 7th state will exist, ready/swapped, along with blocked and swapped. So we end up with something that looks like this as your 7th state diagram for the state of the process. It is, of course, a minor variation of the 5-state model. And it reflects the fact that when something is blocked, it could be swapped out to disk, as well as when it's ready, it could be swapped out as well, and could be swapped in. As before, there are additional exit transitions which do exist but are not shown because it would really clutter up this diagram quite a lot. But this is the basic flow that we could imagine a process will transition through while it is actually executing throughout its entire life cycle. For the most part, we think in this course about whether a process is ready, blocked, or running. The details about it being terminated and swapped and what have you are much more handled by the operating system, and so I expect that you will revisit those kinds of things in a future operating systems course, should you take one. But we will frequently think about whether a process is blocked, if we can unblock it, if it is ready, and we have to remember that a lot of the transitions here are not controlled by us as application developers, but are controlled by the operating system. When a process that is ready is selected to run, that is a decision of the scheduler. It's nothing we can choose directly. Getting blocked is usually a side effect of some system call that we want to make. We want to acquire a resource, but the resource is busy, or the resource is not available immediately, and that ends up blocking our process. And we have to know that this could happen and be prepared to deal with it. So the variant of the 5-state model, it just changes the admit transition. So it says by default the new process doesn't start in memory because it does take some work to actually load the executable and get it started. And we added our swap in and swap out transitions, as well as another unblock. And as in the 5-state model, there are those additional exit transitions that move it to the terminated state from basically anywhere. So this high-level overview of what is actually going on with the process might not seem super informative as to what's going on in Unix, but it is sort of some necessary background for our next topic, where we're going to talk about what do processes actually look like in Unix, and how do we work with them, and how do we use them effectively. So we'll pick that topic up over in the next video.